Hey everyone, welcome to my CFD project video. Today I'll be walking you through how I simulated heat transfer inside a shell and tube heat exchanger using ANSYS Fluent. Whether you're brand new to CFD or just curious how heat actually moves inside industrial equipment, this video will give you a clear, beginner-friendly explanation. So what is CFD and why it matters? Before jumping into the problem, let's quickly talk about CFD. Computational fluid dynamics is all about using numerical methods to simulate how fluids flow and how heat transfers through them. Engineers use CFD to predict thermal behavior long before any equipment is actually built. In the case of heat exchangers, CFD helps us understand temperature distributions, pressure drops, flow recirculation, and whether our design will actually perform efficiently, all without wasting time or material on trial and error manufacturing. In this project, my goal is to simulate the heat transfer process between a hot fluid flowing through the tubes and a colder fluid flowing through the shell. I wanted to visualize how the temperature and velocity fields develop inside the exchanger and evaluate whether my design and assumptions produce realistic results. This helps any beginner understand not just how a heat exchanger works, but how CFD can be applied to analyze real thermal systems. Alright, let's begin by opening ANSYS Workbench. The first thing we need to do is go on the left bar and click on Fluid Flow Fluid. On the Workbench project page, right-click Geometry, then select Import Geometry. From here, I'm selecting my 3D model heat exchanger file. Now right-click on Geometry again and choose Edit Geometry in Design Modeler. Once Design Modeler opens, the first thing we want to do is click Generate. After generating, expand the tree where it says 2 parts, 2 bodies. Click on each body and change its type to fluid instead of solid. This is important so Fluid recognizes both regions as fluid domains. After switching both sides, click Generate again to update the model. Now we can close Design Modeler or just leave it open. Either way is fine. Next, back in Workbench, double-click on Mesh to open the meshing window. Once the mesh application fully opens, click on Mesh in the tree. For this simulation, we will use a less aggressive element size to keep things stable, so set the element size to 2.5 millimeters. After applying that, go ahead and click Generate Mesh. You should now see the complete mesh for the heat exchanger. Now we will label the boundary conditions. Switch to face selection mode. Rotate the model and click on each tube side inlet surface and name it Tube Inlet. Do the same for the opposite ends and name those Tube Outlet. Next, move to large openings on the shell side. Label the top opening Shell Inlet and the bottom opening Shell Outlet. Once everything is labeled properly, click Update and then you can close meshing or leave it open. Return to Workbench and now double-click Setup. A window will pop up. Make sure you select Double Precision and set Solver Process to 4. Click OK and wait for Fluent to fully open. When Fluent fully opens, the first thing you'll see is a setup window. Click on Models, then click Energy and enable the energy equation. This is required for heat transfer. Now go to Materials, click on Fluid, then select Air just temporarily. Next, click Fluent Database, scroll down to find Water Liquid, then click Copy, and close out of the database window. Now go to Cell Zone Conditions. Select the fluid region, change the material name from Air to Water Liquid, and apply. Now expand mesh interfaces and click on contact regions. Change the interface type to coupled wall. Then click apply and close. Go to boundary conditions and click on shell inlet. Set the velocity magnitude to 0.3 meters per second. Under thermal, set the temperature to 300 Kelvin, click apply and close. Next, select tube inlet. Set the velocity magnitude to 0.3 meters per second and change the thermal temperature to 500 Kelvin. Click apply and close. Now go to Solution Initialization and click Initialize. Next, click on Surfaces, then Plane. Choose XY plane and set Z equal to 0. This creates a cross-sectional plane so that we can animate. Now go to Calculation Activities, then open Animations. Click New Object, then Contours. Change the field to temperature and select the plane we just created. Then click Save Display and close the window. Make sure the contour object is selected and click Save. Now click Run Calculation. Set the number of iterations to 30 and hit Calculate. After the run finishes, go back to Animations and click Playback. Set the end frame to 200 and then change the output format to MPEG and click Write. This will generate your animation file in your project folder. To see the final numerical results, go to Reports and then Surface Intervals. Select your inlets and outlets, set the area type to Facet Average, and choose Temperature as the variable. Click Compute, and then this will show all the inlet and outlet temperature values at the bottom of the screen. We started with a shelf side inlet temperature of 300 Kelvin and a tube side inlet temperature of 500 Kelvin. After running a simulation, the model predicted a shell outlet temperature of 316 Kelvin and a tube outlet temperature of 495 Kelvin. That means the cold shell side fluid warmed up by about 16 Kelvin, and the hot tube side fluid cooled down by about 5 Kelvin. So there is heat transfer happening. Energy is moving from the hotter tube fluid into the colder shell fluid, just like we expect in any functioning heat exchanger. So overall, the heat exchanger does work, but based on the final temperatures, it behaves like a low effectiveness heat exchanger. It transfers some heat, but not nearly as much as a real industrial shell and tube system would. What this tells us is that the design as modeled is thermally gentle. It's useful for demonstrating CFD behavior and visualizing the physics, but it wouldn't perform strongly in real-world applications where large temperature changes are required. And that wraps up the CFD simulation of our shell and tube heat exchanger. We imported our geometry, built the mesh, set up the physics in Fluent, created the slice plane animation, ran the transient simulation, and evaluated the final temperatures. Even though the heat transfer we observed was relatively small, this project demonstrated the entire CFD workflow, from geometry to meshing to results, and it highlighted how much geometry, mesh quality, and solver setup influence accuracy. If you found this video helpful, feel free to like, comment, or ask questions below. Thanks for watching, and I'll see you in the next one.